When disaster strikes, power lines fail, and darkness spreads, rescue demands tiny robots that can navigate through cluttered scenes, but without light, cameras fail, and heavy sensors like LiDAR are impossible to carry. And so, in our search for answers, we look to nature. Deep in the ocean, the cuttlefish thrives where little light remains. Its secret lies in its eyes, shaped in a striking W, an adaptation that gathers the faintest glimmers. Inspired by nature, we present AsterNav, an optics-driven passive computation approach for quadrotor navigation in total darkness. Videos are inverted in intensity for clarity. The system combines an IR camera fitted with a coded aperture lens, paired with an IR dot emitter. The dot emitter projects an IR pattern onto the scene. Captured through the coded aperture lens, each dot's blur encodes depth, which our model decodes into real-time dense metric depth maps. Training on blur patterns captured at known depths is key, enabling our model to adapt zero-shot to real scenes. Random crops from these patterns are overlaid onto everyday images. This creates synthetic training pairs of blurred dot overlays and their corresponding depth maps. In this way, the model learns to read depth from blur itself, so it can generalize to entirely new scenes. Our model, AsterNet, is trained on these pairs to decode depth from blur. Running at 20 Hz on a Jetson Orin Nano, it produces dense depth maps in real time. Using a potential field planner with the predicted depth maps enables autonomous quadrotor navigation in real-world scenes with illuminance as low as 1 millilux, which is similar to starlight on a new moon. In this indoor scene, the quadrotor navigates through a complex arrangement of boxes and cylinder-shaped obstacles. Our robot dodges thin obstacles, like a 6.25 millimeter thick rope, effortlessly. And never seen before, objects covered with black matte sheets in a completely dark scene are also dodged using vision only. We then show the capability of AsterNav in cluttered outdoor scenes, with scene luminosity levels of 0.1 lux. Without any scene-specific training, our approach allows the robot to navigate autonomously through these environments. We tested our approach for high speed as well, touching 3.5 meters per second while dodging obstacles. We hope to see our work laying the foundations for vision-based navigation in extreme conditions with passive computation. Thank you for watching.